Good day, everyone, and welcome to the webinar for Amazon Aurora, Best Practices for High Availability. My name is Peter Thawley, and I'm a Principal Database Solution Architect in the Aurora and RDS engineering team. I've been at AWS now for about 2 years, but I've been using relational databases since the very early days of the client-server period in the kind of late 1980s and early 90s. So today we want to talk about a number of topics, but all revolving around high availability and resilience. So the first thing I'd like to do is just to set the stage for everyone, do a brief introduction of Amazon Aurora, just to make sure everyone is level set at the same place. Then we're going to go in and talk a little bit about Aurora's architecture and how some of those fundamental elements provide the kind of high availability and resilience that customers are looking for. Next, we'll move into the database specific areas and techniques that Aurora provides that you can leverage to improve availability and resilience. We'll cover cross-region disaster recovery considerations, and finally close with looking at what you can do at the application side to improve availability. And then, of course, we'll wrap up and have some quick Q&A. So let's begin the journey. So historically, right, I mean, relational databases have been around literally forever, right? I mean, they were invented in the 60s. But if you think about the core ones that are available today, right, most of them were designed in kind of the mid 1980s and early 1990s. And if you think back to those periods of time, we didn't have multi-core chips. We didn't have threads and operating systems. NUMA wasn't invented yet, and we were still using rotating REST disks. So databases were designed with much different things in mind, right? And if you look at all of the layers in a traditional relational database, lots and lots of diverse and complex functionality, and it was a single really code base, right? Single monolithic stack that had very tight dependencies between the code and the data structures that implemented these things, right? And so, you know, many people in those early days really looked in a lot of different ways to improve not just performance and scalability, but also availability and resilience. People tried sharding at the application layer, breaking up a database into multiple independent databases that the application was aware of. Then some smart people took a look at shared nothing architectures where really the application didn't have to know about the different databases, but the database layers were coupled at the SQL layer. Then kind of in the mid 90s, Oracle and Sybase and some others started looking at shared disk technologies where you could really couple at the storage layer, but that required a lot of work to do in the caching and transaction management layers. It turns out that that last approach, that shared disk approach, really has some great advantages for availability and resilience, and we'll talk more about that layer later. But the challenge was that this was all limited by this sort of monolithic design where the SQL layer, transactions, everything all the way down to storage was implemented in the same process. So let's sort of reimagine what would a relational database look like if it were built and designed for the cloud, right? Well, you'd probably break it apart. You'd break apart that whole stack that we just saw, and you'd build something that can scale up, it could scale out. But most importantly, with respect to availability, is self-healing, that there's a lot of automation built in the cloud and in the database to be able to identify problems and fix them without any sort of application or system outage, So this is where Aurora really shines, right? It took a service-oriented approach to relational databases. And so what we did was we moved the whole transaction logging and storage layer into a separate multi-tenant, purpose-built log structured storage engine that really is designed from the ground up to be able to offload database recovery and storage. Then we would integrate with other AWS services. So things like key management for encryption, and Route 53 for DNS type services, and a variety of others, so that we could offload the database as much as possible from doing things that didn't service the core goal of database applications and high availability. And then we'd wrap it up in a managed service, right? Using, in this case, Amazon RDS to take care of all of the heavy lifting of the routine stuff, push button HA, push button disaster recovery, all those sorts of things. So really, Aurora is an enterprise cloud-native relational database that gives you the speed and availability of the high-end commercial databases, but with the simplicity and cost-effectiveness of open source databases. It provides drop-in compatibility with both MySQL and PostgreSQL. So you can choose the database that fits your needs the best, and offers really simple pay-as-you-go kinds of pricing. Okay, so now let's get into kind of the nitty-gritty. So if you think about availability in the old days, right? On the left side of the screen, you kind of see how it works in RDS today, or if you were using, SQL Server or Oracle or some of the more traditional databases, right? You tended to scale out by creating replicas, but these replicas were independent copies of the database, and they had to be maintained using some sort of replication, database replication kinds of technologies. In RDS, we have a multi-AZ standby model that uses synchronous page writes, as we show here, but traditional databases would use asynchronous types of database replication to be able to maintain those independent copies and keep them in sync with the primary database. Okay, and that was state of the art really since, frankly, the very early 1990s. Aurora took a much different view, right? We looked at what shared disk cluster architectures like Oracle RAC and Sybase Cluster Edition provided, which was the ability for nodes, compute nodes, to directly connect to each of the storage layers, right? And that way you could provide almost instantaneous scale out, right? To be able to add a read node almost instantaneously. You contrast that with the old approach, and it might take hours for a new copy of the database, especially if it's large, to be provisioned and synchronized with the primary. So this is the area we're really going to focus on today, is this shared storage architecture and how that provides a lot of basis for these capabilities. So let's dig in initially to this area and look at the storage engine, right? Now, the first idea here was really to be able to offload the database from having to do all of the work around storage processing and managing pages and buffers and all of the nitty-gritty stuff. And what that does is it frees CPU for the database to run queries, SQL queries, right? But more importantly, it reduces a lot of the code path and complexity in the database engine, and that makes it simpler and more reliable. Secondly, Aurora only sends log records to storage, right? That's the only way in which changes are sent. We don't have to worry about full pages and buffers in terms of writing data to the database. For durability and availability, though, one of the biggest innovations is that the database simultaneously writes these updates, these inserts, to 6 different storage nodes across 3 availability zones. And we do that to ensure resilience and durability of your data. This allows us to handle what we characterize as an AZ+1 failure. In other words, I can lose an entire availability zone and still maintain read and write access to your applications, right? Even an AZ+1, let's say, for example, one of the storage nodes goes down in one of the availability zones, as well as an entire AZ. We can still provide read access, and we'll go into some of the details around that shortly. We use a quorum-based model that we heavily optimize for latency. So if you look at write latency on Aurora versus write latency on an EBS-backed RDS engine, you'll find that they're effectively the same, right? Even though we're writing the data to 6 different storage nodes across 3 AZs. And we've done a lot of work in optimizing the network in order to enable this sort of innovation. As we talked earlier about, though, when it comes to availability, it's super critical to have continuous monitoring and repair, right? As our CTO likes to talk about, things fail. They fail all the time, right? And so the key for resilience and high availability is not only to build in resilience into the architecture, but have routine monitoring and management that allows you to predict failures, to look at capacity issues in storage, hotspots, and to be able to proactively move things around to ensure that a storage node doesn't fail, or that a sector on an SSD drive isn't going bad and needs to be offloaded, right? So a lot of that continuous monitoring happens in the background. You don't even see it, but it's running 24 hours a day, 7 days a week. We also use this notion of segments, 10 gigabyte segments, as a unit for repairing or rebalancing. So if we find a storage node or a particular SSD device is overloaded, we can move these segments around to rebalance or to even repair things. So super innovative area, this storage engine, and it really provides a lot of the basis for the high availability that that we're talking about. The other thing we do in the storage layer is we offload backups entirely. So DBAs no longer have to, set up cron jobs that go off and back up their database, every 5 minutes. This just happens continuously in the background from the underlying storage layer. So this area, this distributed storage engine, is really a significant enabler of innovation for both performance, scalability, and availability and resilience. So we'll look quickly at write traffic in Aurora. Mostly in the context of high availability, I really wanted to draw your attention to this area in here. Let me get my pointer working. So whenever we do writes, as we talked about, we write these log records, from the writer node over on the very left side into all of the storage nodes. And as we said, we do these simultaneously so that you still get very quick latency of your write activity. However, it's really important to recognize that these reader nodes are also reading that same storage, right? And they're buffering pages in cache. So anytime a writer node updates some piece of information, we need to do a quick validation to understand if that same page, if that same piece of data is already cached in some of the reader nodes. And if so, to transfer those log records and have them applied in these other reader nodes to keep the consistency of the database intact, right? From an HA perspective, though, it's important to recognize that we do a lot of these block level operations, fault repair, garbage collection. We do this all in the background in these storage nodes at the very bottom. We don't have to overload the database layer from doing a lot of work that otherwise it would have to do. If we dig in a little bit into each storage node, I also wanted to share a little bit about that workflow because it has some impact on high availability. As we see, log records are transferred from the writer node into a storage node, which is this whole block here. This is one storage node. And they come into a queue and they update this queue, which basically means we persist them on disk. So they are now stored reliably on an SSD device as a log record. It's at that point that we can acknowledge back to the application the fact that that write is persisted reliably. Then we can do a whole bunch of stuff in the background. So now the application is basically happy and can go off and do more work. But in the background, we do all of this work. And some of that work, as it relates to high availability, is doing things like in step 6, 7, and 8 to stage these log records and write them into Amazon S3 as part of our continuous backup process, to periodically garbage collect these old versions so that we can shrink the size of your storage and keep it as cost effective as possible. And most importantly, to be able to validate these CRC codes, right? These checksums that we maintain on the blocks to ensure that there isn't any sort of hardware or storage level corruption that could potentially occur. If it does, it's not a problem, right? We've got 6 copies so that we can go back and revalidate the right page data and ensure that corruption doesn't really become an issue that you as the customer has to deal with. All right, so let's dig a little bit into the database layer now and some of the techniques that customers should be thinking about with Aurora to ensure the highest levels of availability and resiliency. So first is really the minimalist approach, right, to resilience. Every database provides mechanisms to do backups. With Aurora, it's continuous. So we're always just pushing data into S3. Today we support, up to 35 days of retention, and you can recover at worst up to the last 5 minutes point in time. Oftentimes it's a lot shorter than that, but from an objective, we strive to make sure that it's at least within 5 minutes. Customers can also take their own user or database snapshots, right? These snapshots, just like backup, because they're done by the storage engine, have no performance impact. And what we tend to advise customers for, especially today in this age of ransomware and concerns about security, is copy snapshots off to other regions, share snapshots with other AWS accounts, so that you can always have a copy of your database that is safe in another region, safe in another account, encrypted with a different encryption key. Okay. We're doing quite a bit of work these days with our AWS backup service for both long-term and policy-based data retention. So many customers who are in financial services or other regulated industries have long-term retention requirements, 3 years, 7 years, in some cases forever. So AWS provides some very innovative policy models to allow customers to choose, their retention periods and ensure that they always have copies meeting the regulatory environment that they depend on. Restore times generally tend to depend on volume size. So, obviously a 20 terabyte system will restore a little bit slower than a 2 terabyte system. And restores always create a new cluster, right? So you always have that sort of fallback perspective. But as we said, this is kind of the minimalist approach, right? The least you can do or should be doing to ensure recoverability of your systems. Most customers that have strict high availability requirements utilize Aurora reader nodes as failover nodes and as scale out nodes for read performance, right? So from a performance perspective, obviously you can create up to 15 read replicas in Aurora within the same region. We'll talk about cross-region and disaster recovery things later. But these read nodes, again, they attach directly to shared storage. So it becomes almost instantaneous, right? You can generally attach a new reader to your cluster in usually a matter of minutes. And for the most part, the delay is really allocating a new instance in the EC2 world to be able to attach to storage. We've talked a little bit about buffer caches being kept coherent by applying these log records, but from an availability perspective, we have a reader endpoint that basically uses DNS to do load balancing across the read nodes. It's kept in sync by Route 53 and the other components of the system in real time. And what a lot of larger customers do is use what we think of as custom endpoints to be able to isolate, very workload specific types of workloads to specific readers. So for example, you might have some reader nodes that are servicing very fast primary key lookups, right, that you really want to make sure operate, in milliseconds. Whereas other workloads might be more analytic or reporting oriented, and you might want to offload those onto entirely different read nodes because those tend to be very long-running types of queries, and you don't want them impacting your OLTP kind of primary key lookup type queries. So, but from a performance perspective, very strong capabilities around using reader nodes. However, for availability and resiliency, they become super critical to use. First of all, failing nodes are automatically detected. We have at the top here this database and instance monitoring capability. So these are always issuing queries, if you will, as heartbeats, right, to all of the nodes in the cluster so that it can detect quickly if something fails and can automatically restart, whether it's a process or whether it's an entire instance, right? We also have this notion of failover and failover priorities that allows you to designate maybe one of these nodes as your primary standby node, right? And so if there's a failure in the primary write node over here, this will be the node that will be failed over for write activity, right? We'll talk a little bit later about this concept of cluster cache management that keeps this standby node, if you will, failover node, keeps the buffer cache of this and the writer very closely synchronized to ensure that you don't really have a stall in performance after a failover of any significant time. So how does that work? Well, pretty much any read node can be promoted to the writer node or the primary node, right? And when you create reader nodes, there is an attribute that we use that we call failover priority, which allows you to designate the priority of different reader nodes in terms of failovers. So you'll see in this case, we've got the old writer, which has failed, and it will fail over to the lowest failover priority of all the reader nodes. In this case, there's another one designated as failover priority 0. The cluster endpoint, that is the writer endpoint, will be changed to reflect the new instance. And if that one were to fail, it could then fail over to the next lowest failover priority, right? Once a node fails, they are replaced and they come back online as reader nodes. So you'll always be kind of guaranteed that if your cluster is 3 nodes, that you'll always have 3 nodes, albeit perhaps with a little bit of weight. Aurora also adds some capabilities to minimize failover time that we call survivable buffer caches, right? So if you think about the more traditional Oracles and SQL servers of the world, the buffer cache is kind of part of the actual database process. If the database process were to die for some reason, that cache goes away. It's basically uninitialized and has to be rebuilt by reading data into that cache continually. Aurora has moved that cache out of the database process entirely so that they are treated independently. If the compute instance restarts, the cache and all of the contents of that cache continue to exist. And that way we can reattach those two and you have a warm cache even after a database restart, whether it's a crash for some reason or whether it's a upgrade that has to happen. This lets the database resume fully loaded operations much more quickly than in previous implementations. And we also have this cluster cache management capability, as we talked about, that keeps the buffer cache of the failover node in sync. And we do that by basically shipping page addresses from the writer node here to the failover node so that the failover node can do the reads to pull those buffers into cache and keep it almost completely synchronized. What that tends to provide is a failover. So here, if you see the database is running and it's running fine, and then for some reason it has a problem, it has to restart. Without cluster cache management, it could take minutes before the cache is built up in a way that restores the kinds of performance that it was seeing before the crash or the restart. With cluster cache management, we can keep that time to an absolute minimum, about an order of magnitude faster before the cache hits a point where you're able to sustain kind of the queries per second that you were seeing before the failover, right? So super useful capability. You only want to do this on one of your failover nodes because it does consume some CPU of both the original writer as well as the failover node. Another area to explore when it comes to high availability is really about load balancing workloads, right? And there are a lot of people that think about availability more broadly than just failures and how to recover from failures, but really they think about it in the context of how do I maintain a certain level of service to the applications, right? That are connecting to that database, and that could be in terms of supporting some number of users, hundreds, thousands of users. That could be maintaining a certain profile of query response time. And the reality is certain workloads like analytics workloads and reporting workloads tend to consume a lot more resources than traditional transaction processing applications where you're doing insert, update, deletes, or you're doing searches of the data by primary keys. Well, one technique to think about when it comes to availability is to segregate these workloads, to have your OLTP systems running directly on the certain nodes in the cluster, but also on the storage side, there also becomes some benefits to doing something we think of as database cloning. For those of you that are familiar with copy on write technology, so these would be with things like Delphix, as an example, one of AWS partner. The idea is to be able to create a copy of the storage without incurring a huge amount of costs, and to direct certain workloads to operate against those clones. So here what you see is we've got the primary Aurora storage volume at the bottom. This is what your production OLTP systems are using. But I can create a clone almost instantaneously and allocate some instances, perhaps for analytics and reporting workloads, perhaps for QA applications that want to run directly against production data. And if these workloads issue writes or changes, we're not changing the underlying production data. We're actually cloning a block and changing that one block. So very cost efficient, very performance efficient in how you can run certain workloads without really impacting the performance and availability of your underlying storage volumes. Right, great technique to consider as you move forward. So let's think a little bit now about placements, right? So if you think about AWS regions, really all of them have at least 3 availability zones. Some have more, right? US East 1 has 6, US West 2 has 4, AP Northeast 1 in Tokyo has 4. And that will probably grow. We'll probably see over time more regions expanding capacity and having more availability zones. But if you think about AWS services and resiliency, many of them are designed for 3AZ resiliency. So think about Aurora Storage writing the same data, 6 copies across 3AZs. Lots and lots of examples of that in AWS. But it's really important that you, as the customer, sort of proactively start thinking about that. So for your most business critical systems, you should be thinking about how do I plan for failures that might happen at virtually every level of the stack and infrastructure, right? So all in the name of improving resiliency and continuity, right? So, first of all, placing your compute instances close to Aurora storage is a good thing from performance, but also an important thing from an availability, right? If you have a reader node in an AZ that goes down, that reader node's going to go away, right? If that's the only AZ you have nodes in, then you're going to have to, or we're going to have to spin up new nodes in different AZs, and that's going to delay recovery time, right? So think in advance about your virtual private connectivity, your VPCs, right? Think about your security groups. Make sure that you have sufficient AZs in your VPCs and security groups to cover failure scenarios, right? We saw issues in the past where an AZ goes down, but we couldn't allocate a new instance there because their VPC didn't include that other AZ, right? So make sure you think about having 3 AZ connectivity in your VPCs and security groups. In AWS regions where there are more than 3 AZs, use the CLI API called Describe DB clusters to see where your Aurora storage volume has been placed, right? If you're in US East 1, it might have been placed in, 3 AZs that maybe you don't have included in your compute layer VPCs for your database instances. So super important. And even broadly, if you're a large customer and you've got hundreds of databases that you have to oversee, think about how you might segment them across these different AZs to minimize the blast radius that might occur if one AZ goes down entirely. Okay, and again, using the CLI API create database cluster, you can really fine tune where both your storage clusters are placed as well as your compute clusters are placed. Okay, so let's talk a little bit about global database now, disaster recovery and business continuity. Okay, Aurora features something that we call global database. And this uses asynchronous replication of transaction logs, just like you have in region, but to be able to store copies of your cluster in other regions. It's highly optimized for Aurora. It uses the AWS network backbone so that we can have super low WAN latency and high availability, as well as complete isolation from the public internet. We use encrypted connections from one region to another and multiple sessions, multiple TCP/IP connections to reduce the jitter, right, and keep the latency super low. And you can have up to 5 secondary regions for copies of your database. So some key features we've talked about: very low replication lag across regions. I did a benchmark for a big bank down in Australia a while back, which needed to have copies of their data in London as well as in Northern Virginia. And even running at very high load, roughly 100,000 SQL statements per second on a 12XL sized instance, we were still seeing latency to London that was in the 500 to 600 millisecond range, and to Northern Virginia that was in the 350 millisecond range. So that AWS backbone provides very low latency under normal operating kinds of scenarios, right? Also, the nice thing about global database is it provides some optimizations for failover. In some cases, we have a managed planned failover process. So for customers that have regulatory requirements and need to sort of rotate the regions to prove to auditors that they can operate in different locations, we have a 0 RPO, so 0 data loss, and very low RTO on the order of minutes process that you can use to kind of rotate which region is considered your primary region. We also have unplanned failover models with very low RPO, as you can tell from my previous example of replicating from Australia to London with replication lag of 500 milliseconds. You can keep the RPO really very, very low. And today we use kind of a detach and promote process. There is some potential, you might lose, a few tens, a few hundreds of milliseconds, maybe a few seconds worth of data. But it still requires a human or at least some sort of application logic to decide, when to promote, because there's obviously lots of other things you need to think about in a regional failover, such as where is your application stack running and all that. So lots of capabilities to improve resilience across region. We also have, at least in the Aurora Postgres capability, something we call managed RPO, which strictly enforces. So if you as a business say, I cannot lose any more than 20 seconds worth of data, we can put a limit on that to ensure that that will never happen. It does stall commit processing on the primary, but it is really most useful for those regulatory environments that have very strict regulatory rules that need to be enforced. This is effectively the architecture. We've got on the left side, we've got our primary region over here. We've got a writer and some readers. And for each region that we need to replicate into, we've got an outbound replication engine that is hidden from you. You don't have to manage it. It just sort of runs in the background, has built-in monitoring and health monitoring kind of built in to make sure that it runs constantly as well. This replication layer basically sends transaction logs, which we follow the same paradigm we do in the primary region to update Aurora storage, update the caches of reader nodes. So super low replication lag, very fast recovery if you need to fail over to a different region, generally on the order of a few minutes, and very high throughput as we've seen. There are some customers that really have very strict high availability requirements and need to be able to write from any region into the primary region. And so rather than have the application maintain connectivity from the application stack to the primary region, we've provided a write forwarding model that allows the application to send writes to any read node in any region and have that write forwarded back to the primary region. Again, all in the name of improving availability during big global deployments that many customers have. There are a few challenges that we should talk about around consistency, because the writes are being effectively sent to the primary node here and then have to be forwarded back. There is some latency that has to be dealt with, but there are consistency models that we provide mechanisms for. Today, this is currently available in Aurora MySQL and will be soon be made available for Aurora Postgres as well. Okay, so let's dig in a little bit now to the application layer optimizations. And if you look at failover, one of the largest areas that impact how long it takes to fail over a database is DNS propagation, right? And you can see here, kind of a significant time in most traditional databases, even in Amazon RDS databases, that DNS propagation, can generally take around 30 seconds. Now, normally in the more traditional databases, that DNS propagation is usually faster than running recovery on the databases when you bring them up, so you don't really see it. But in Aurora, because the storage engine handles recovery under the covers as part of the storage engine, running recovery is generally lightning fast, right? Generally under 10 seconds. So now all of a sudden, DNS propagation becomes a bigger component of failover time. And so there's a few ways to manage that, right? For example, if your application caches DNS addresses as opposed to making iterative calls to the DNS service, you can set your time to live values on the network layer sufficiently small so that the DNS gets updated more quickly. There are also two other solutions that provide mechanisms to remove this issue. One is something we call RDS Proxy. RDS Proxy is a connection pooling proxy service, fully managed for both Amazon RDS and Aurora databases. And so your applications connect to a proxy. That proxy provides a lot of valuable benefits from connection pooling and improved security. But in the context of failover, it keeps track of your failover targets and maintains a lot of this information inside the proxy service so that you can fail over much more quickly to an Aurora database or an RDS database. So thinking about this, from a performance standpoint, apps connect to the proxy, and the proxy can determine that a database has failed and can open connections to that database even in advance of the failover. And you can see in this chart here, looking at Aurora MySQL, the failover time using a proxy compared to even an optimized MariaDB driver is generally an order of magnitude faster. So app connections are preserved, transactions can be queued, so there's a lot of valuable benefit to eliminate errors to being returned to the application layer. We can detect these failovers much more quickly. We generally see failover time is somewhere between 66 and 100% faster. And there's a lot of innovation happening in RDS Proxy. We're doing a lot of things to have single endpoints so that you can really just connect to the proxy and have the proxy split reads versus writes to the primary versus the read nodes. We're also looking at a lot of workload-based query routing to be able to route resource-intensive analytic queries to different nodes. Again, based on policies and other techniques. And in preview, we've also released a native JDBC driver for both the Aurora Postgres and Aurora MySQL capability. And there are some applications, some use cases that we need to maintain this high availability sort of connection state in the application itself, rather than in a proxy layer, right? Perhaps they don't need connection pooling. Perhaps they just want to streamline the layers of their infrastructure. And so we've built effectively connection high availability into the driver layer itself. You can see some architecture on the right side. But it all starts really with this topology cache that keeps track of write nodes, all the reader nodes in your clusters, and separates the logical connection to the application from the physical connections to the database. So we can manage that. We have a state machine that basically handles failover as part of the driver. Again, all in the spirit of reducing um, failover times to the application. And again, just like we saw in RDS Proxy, we expect a lot of innovation in this area, query routing, both for reads and writes, as well as workloads as well. The JDBC driver, this native driver that we talk about, is open sourced under a BSD2 license. So you're free to go to these GitHub sites, pull it down, look at it, play with it, enhance it to do what you need it to do. And obviously, if people want to contribute, we would love to have contributions in this area. So in closing, in summary, I wanted to introduce this notion of a shared operational responsibility model, right? When you think about all the things we've gone over today, as a managed service, a lot of the secret sauce for resiliency and high availability is kind of hidden from you. You don't have to do a lot because it's embedded in Aurora or it's embedded in the RDS control plane, right? So things like distributing storage across 3 AZs for durability and resiliency. Having reader instances that can be set up across AZs and maintaining cache coherence between those, having optimized recovery and both proxy and driver options for fast failover, right? A lot of that is kind of hidden. But as we saw today, there is also some things that you need to do or should be thinking about in designing your use of AWS infrastructure for the flexibility, in case there's a failure event, right? A full AZ outage, right? We talked a little bit about ensuring that your VPCs and security groups are designed for 3 AZs. We've talked a little bit about aligning your reader instances and the app stack for the availability zones where your Aurora storage has been placed. So think about these in advance, and together, all of these can contribute to super high levels of availability for your applications. So that concludes the webinar portion of this. I want to thank you for your time today. I hope it was helpful. And now we have some time for some questions.